I think last time we start talking about the classifications. We're done with the regressions. Now we move on to another topic, which is, I think is also really important. And here I'm going to cover three different. The first one is perceptron, and second is support vector machines, which is SVM, and the last one is logistic regressions. So in order to give us the motivations for classification problems, remember I gave you examples like, suppose we or you guys are working at a bank, and whenever you have a customers, you have to extract some kind of features out of it, right? For example, like job or age, whether you got married or not, and anything is going to be features. We don't know which one is more important or not. Using that examples, we derived like here at this moment, and it turns out like omega transpose X and sign functions like positive and negative things. Based on those calculations, we're gonna decide whether we're going to approve or deny the credits. And this is kind of the modeling part. Now we have to find out the omegas like given data set. So now what I want to do is that transfer that modeling part into geometric sense, like omega transpose X, what's the meaning of omega transpose X and things like that. So that's why we here, now I want to put everything. The simplest example would be like in 2D space, because it's easy to imagine and visualize or plot. So I want to show you what's the geometric meaning or physical meaning of omega x's, things like that. So let's start from here. So in line means, so in everything now is in 2D space for simplicity. And I guess in 2D space, probably like this is the communications to represent line like this. So we know that A is slope, B is like intersection in the Y with the Y axis, things like that. And now I want to switch it to, like, this is X of 2 and this is X of 1. And I will say X of 1 minus X of 2 plus B equal to zeros. I mean, these are unknown coefficients. So I want to change it, but I change the notations. And like that. So now I want to use omegas and X of 1 and X of 2 to represent it. And we know that this is linear equation or constraint, whatever, to represent a straight line in 2D space. Okay. Starting from this notation, I want to show what I want to compute the distance from that. So before that, so omega is like omega 1, omega 2, or you can think of as a omega naught, omega 1, omega 2. So actually, I mean, and X, in this case, X is like X of 1, X of 2. With these notations, probably let's say X of 1, X of 2. So I'm gonna mix these two different notations because both of them has some kind of meaning. So I guess from the context, is not gonna like you guys can easily see, but don't be confused too much. All right. So from that, I want to show you guys that this or omega transpose X plus omega not equal to zeros. I hope that you guys see the difference. I mean, these are, look same notations, but like there's this, right? So with that, I want you guys to see what's the meaning of vector omega. So in order to that, suppose we have two vectors or points on the decision line over here, and this is, and like we did that, we know that since these P and Q are located on top of the decision lines, should be satisfied that linear equation or constraint. And we do some math and calculations, things, we reach that point. And this means that omega transpose and P minus Q, which is P and Q is any points, like it could be this way and this way, it doesn't matter, but the vector is parallel to the line that we have. This means that omegas and orthogonal P and minus Q vectors. So whenever you see this or this, omega represent that way. I mean, I would say like 90 degrees. That's the key, the orthogonal or perpendicular. So if the omega is given, we know the direction of the straight line. If straight lines, we can get omegas. But we don't know whether omega is in that directions or in that direction. We don't know yet. We don't know yet. Right? But it's okay. So the conclusion that we can make it out of this is that omega is gonna be normal vector to the line, which means orthogonal. It's gonna tell us the direction of line, right? So that's, now let's move on to, let's go further. I want to suppose that I want to compute the distance from the origin, like say in, again, it's in 2D space. We can extend it to higher dimensions, but just for simplicity, like imagine, or I will do the calculations in 2D space. Suppose we have this kind of, which is omega transpose x equal to zeros, or omega transpose x plus omega not equal to zeros. Distance is from the origin, this is the origins, and I guess this is the distance that we are looking for. And probably say like that way. This is gonna be the distance. Distance from the origin. I guess you guys know what I'm talking. So let's compute that, this guy. And I'm gonna remove that one, erase that. Let's use that one. And we know that this and the D is, and we also know the direction. The direction is omega. So this means that it's the orthogonal, but it's we divide by its length, so it's a normalized, so it's a unit vector of omega, and we want to compute the distance. We don't know yet, so it's unknown. So D is the distance. So I'm gonna set, so let me show you the X. Suppose we have X is over there. So this is gonna be the X factors, right? The vector of X. And we don't know the distance. We want to calculate it. And another constraint that we know that the X, the vector is on top of that line. So should satisfy that one. So we can this computations, and let's do like omega naught plus d is just scalar values, omega transpose omega divided by norm of omegas. And we know that this is what? This is a inner product of itself. So, squared. And we can do that. So this is not, we can compute. That's exactly what we want to have. All right, given any straight lines, we are able to compute the distance d from the origin. And another thing that I want to mention here is signed distance, which means that the distance we can have positive and negative in this case, because that's why I said signed distance. So in that case, like if omega naught is positive, that means there's negative distance. If omega naught is negative, then we're going to have the positive distance. The reason why we have signed distance, probably like this distance and these are going to have different sign. It really depends on omega naught. Okay, so that's how we can compute the distance using that one. Let's think about this. And now instead of computing the distance from the origin, say this is g of x, and any data points, any. In that case, the distance would be like let me show you. Yeah, distance. Let me write it that way. Suppose we have any data points. Doesn't have to be on top of the line. Now the distance is h. I want to know that. So now it's we have in 2D space and straight lines and any data points. I want to compute the distance. The shortest distance will be like that, given this constraint. All right, so let's see how we can do. And we know that x, we can decompose it into, so we know the omega is given, right? And we know that we can decompose it like that. It's parallel to omegas and perpendicular omegas, we can decompose it. So x is like x and these two. And since we know the vector omega, and suppose we have, now I can decompose it like that. And this one is distance d, and we know that these are, we say these are r. You guys know what this one is, d, and this is h, and r is d plus h. And the x perpendicular, the vector is, the direction is gonna same as the omegas, so normalized unit vectors, and the length is gonna be r, like that. I mean, we don't know r, but we can calculate it later on, and we put it in the assign it as unknowns. And this one, let's compute the omega transpose x. Let's compute it. I mean, omega transpose x, x is not on top of the line, so it doesn't have to be zero. And we can plug into x like that. We do these computations. And omegas and x perpendicular. Omega is right there. Omega is these directions, and x perpendicular is that one. So it's if we do the transpose or inner product, it's gonna be always zero. So this term, if we do this goes away, and only the rest term is gonna be like that. So we can do this. And omega transpose x again is same as omega squared. So it's r times the length of omega. Now, this is the equation that we have. And we know that that one is same as that. So we plug into that. And from that, omega naught plus r is, we know that d plus h. And we know the d is from the previous slide, like that. So omega naught plus minus omega naught divided by omega and h. We can compute it, minus omega naught plus h omega norm, two norms. So it goes away, and we know that is g of x. I mean, g of x is not equal to zeros because x is not, doesn't have to be on top of the line. It can be any. So h, the distance from the line, is g of x and divided by omegas. That's the thing that we want to compute it eventually. And also over there, it's signed. G of x, we can have positive and negative. We can have that. So that's what I want to. The h is the signed distance from the line to any point x. So it's orthogonal signed distance from the line. So at least I want you guys to remember this, the formula, because we're going to use that later on. So we know that h now it's g of x and divided by omegas, and we know g of x is omega transpose x plus omega naught. And think about x like here. And we know that in this case, h is zeros, right? For that case, let me plug into this, the formula. We know that x is here, then let me see, h is g of x divided by omegas, but here is 0 because we know that this is 0. Okay. And another one, say we have x over here, and given the y, the vector is in that, for example, and g of x is gonna be positive for this case. So divide by, so any data points. So suppose we have in this direction of omegas, any data points on that distance is positive, like that. On the other hand, in that way, any data points here, the distance and g of x is gonna be negative. Positive and negative. you guys remember we start from the binary classification problems. Binary classification problems. So in the linear classification boundaries, and we want to find out g of x is equal to zeros to satisfy all the data points in data point belong to one class, it will be positive and the other is negative. That's the way set up the mathematical expressions like this. Whether this one is positive or negative, it really depends on the direction of omegas. Direction of omega. If that way, it's going to be positive, it's going to be negative. It's going to be negative. So how do you find the omegas? That's the, right? Remember in the example of the bank and customers, and assume that we don't know omegas. Assume that we don't know importance of each features. We want to find out omegas from the data set, historical data set. That's the machine learning. Instead of or as a users, instead of predefining the value of omegas, predefining the importance of each features, we want to learn the omegas from the data set using the machine learnings. Okay, how do you find the omegas? And thinking about all the framework that we predefined so far, if that's the binary classifications, we have only two classes. All the data in, suppose this is in class 1, will be positive. All the data in another class should be negative. What do you mean by that? So say we have like this one class and another class like this. No, I want to. And again, it's for the linear classification problem, we want to find out the classification boundaries. If we have, suppose this is the boundary that we have, like say is omega is in that direction. In that, this one is positive, 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 all the positive. The problem is that this data point also positive. So we know that this is not a good classification boundary. So that's gonna be out. And like that. Again, and we don't know omegas, but it says this is the omegas. And all the data points here is based on this classification boundaries, gonna be positive. But some are in, but the other is, so this is not a good classification boundaries. We want to find out, say, like that. The direction is doesn't matter whether they that way, because all the data points in one class, in that case, all of them are positive. All of them are positive, and these are all of them are negative, which is good. So this is good classification boundaries, and we probably, this is the omega. I mean, that means now we know the importance, we know all the coefficient, we know all the importance of each feature, which is good. So it's done. All right, that's how we do. And also, remember in Perceptron we did this. So all, if the positive, since we have signed, the labels is gonna be 1. And this is negative signed functions, so it's -1. That's why when you do labelings for the binary classifications for perceptrons, we label it 1 for one class and -1 or -1 for other class. that's how we do it for perceptron. Now the thing is that in perceptron, how you find omegas? It's a perceptron algorithm, and actually it gives us the solutions instead of let us the thinking of how you to find out the omegas. So this is the answer to find the good omega. And let's see. Perceptron implements, compute that one for each data points. Given training data set, we have that. Suppose we have n data points with labeled. Okay. And start from random omegas. We want to find out the omegas, but we don't know yet. So I'm gonna randomly assign any values to omega. And of course, in this it's gonna be it's not perfect. So we might have misclassified data points. Pick that one, which means that this one and the true labels and computed one or predicted one based on the current omega, based on the current omegas. And if we have any misclassed data points, that means the current omega is not the best. Then update it omega with this. Okay, I'm gonna show you, I'm gonna explain it in a minute, but that's the listing is that's the perceptron. Starting from any omega, and we might have misclassified data points. For that misclassified data points, using that informations and updated omegas. Then if you repeat that process, eventually you will get good value of omegas. That's what perceptron says. Interesting, right? And let's see why this is it's gonna work. Let me see. So there are two cases, misclassifications. There are two cases. Say, first one, the true labels is +1. Then, since this is, if this is misclassified data points, that means the corresponding x, and we compute the omega transpose and signed is what? It's misclassified data points. What will be the value is +1 or -1. It's misclassified. What do you think? -1, right? For the misclassified data points. That means here is positive or negative. Is it positive or negative? We have signed functions. Omega transpose x is a positive or negative. We have -1. Anybody? It's assigned functions like that one. All the positive values, it's gonna give us the +1. All the negative values, -1. That means this one, it's negative. It's negative. So remember, omega transpose x is a negative. That means if we do have omegas in that directions and be perpendicular, like g of x is equal to zeros, because we know that omega is give us the perpendicular directions, and the x is x will be the proper location of x, number 1 or number 2. Because we have negative. I said that all the data points on this side, considering the omega is that directions, is positive. Any data point is negative because in the opposite directions. So that means, say, if we have omegas here and we can draw like that. And we know that since this is negative, that means in the opposite direction, this will be like one of the position of x. Now we want to update omegas using this equation. That means in here is true label is, here is 1. So omega plus x. That means now we have two vectors, omega vectors, current omega and x. If we do vector multiplication, additions, this will be new omegas. And if this is new prime, then you can tell updated classification boundaries like that. And this is new omegas. Now looking at the x in same side. So it's a positive. Omega prime transpose x is positive. So it's gonna give us y is same as +1. You guys see what I'm doing it? Starting from random omegas, and if for any misclassified data points, update it using this, and we can correct the omegas like that. And we have to check in this case as well, but I'm not gonna do it I want you guys to thinking about thinking about it at home. So okay, I'm gonna skip that one. I'm going to skip. So Perceptron is kind of iterative way. So randomly assigned omegas. So because we have to have some value of omegas. And for any misclassified training points, we want to update it. And repeat until all the data points are satisfied. And for here, if you have any misclassified data points for the current linear classifiers, probably after the iterations, probably like we have probably. Then let me ask, suppose we have in that case, I think out of Perceptron, we're gonna have this one as a classification boundary, right? And what if? Let me ask. What if we have any data points here? Do you guys think we can get linear classifier out of Perceptron? What do you think? There's no way that we can classify all the data points using linear boundaries. So in that case, the iteration process is going to keep doing it. Right? So we cannot. So the conclusion that we can make it for perceptron, we have to have linearly separable data set. If we do, then we can get some good classification boundaries using perceptron. Otherwise, we cannot. Right? So another way that we can represent the perceptron is this is diagram of perceptron. And we have X and Y. We're going to have multiple data points as a training data set. Those are the given. Out of that data points, say perceptron, we can compute omegas. We can compute omegas. So input and output are given. The thing that we want to find out, the unknowns that we want to find out, the parameters that we want to find out is omegas. Here. So actually what over there we have X. This is summation of X omega I xi and put it in the sign functions, whether it's positive or not. And the predicted one might be +1 or -1. For each data inputs, we do have corresponding actual outputs, true labels. Over there is let's say it's a compare. We do comparison. Whether the predicted one and the actual ones are the same, we don't need to do anything. If it's different, then we have to update. We have to update based on, we have to update it like that. This one. That's perceptron. It's extremely similar to gradient descent. It's extremely, here you can think of as a gradient, either +1 or -1. This one is acting like gradient. Okay, this is diagram that to represent perceptron. And again, here I'm going to skip it. And the next thing is that how can we implement it in Python? Right, so we randomly generate it for the training data set. So it's, as you can see here, it's red and blue and C of 1 and C of 2. And as you can see, all of them are linearly separable. So I guess we can get some linear classifiers using perceptron out of this linearly separable classes. So unknown parameters is omegas. So we do that, and this is perceptron. And this is core part. And say if X is misclassified, do this kind of update. And actually, we have to do some stopping criteria, but in order for the simplicity, I said that repeat many times. And this is not the correct implementations, but I guess in order to see how the perceptron works and how the perceptron algorithm is coded is good enough. And if you do and plot it, you will get this kind of, I mean, this is, I made it out of that is animations. So it's omegas is keep updating. And whenever you have any misclassified data points, just keep updating. Now, this is what we got out of Perceptron. And you can see there's no misclassified data points, which is good. And if you repeat it, because we start from the random initializations for omegas, it's slightly different. But again, as you can see here, it's a good classifier. There's no misclassified data points. What do you think? Do you think it's good or not? At least we know that this perceptron, if for linearly separable case, it works. And this is one of the possible outcomes that we can see. But I mean, for me, I guess this one like will be better than what we got out of perceptron. If we have two data points like groups, and probably like I want to put the classifiers probably in the middle, but it turns out that the output of perceptron is not. So that's why we have better method, better approaches. And so, okay, that's why I put the perceptron first for the classifications. And it's good to understand what's the classification problems and things like how to compute the distance from the data, any data points from the line, and utilize that ones to find out at least the linear classifiers for linear separable classes. But at this moment, at least we can make some kind of conclusion that we can do better. We can do better. That's why we have two other methods are coming, which are like SVM and logistic regression. Okay, so this one is kind of motivations for SVM. And another way, actually, we don't have to implement it in perceptrons, like since like we have Scikit-Learn and imported the linear models and perceptrons, and we do like fit, we can get. All right. So for the machine learning, Scikit-Learn, you have all the method that you have. It's already embedded in, so you don't have to program it by yourself. So again, it's classification boundaries in higher dimensions is going to be hyperplanes. Is that the best separator? Like probably not. Perceptron finds one of the many possible hyperplane separating data set if one exists. The second question that we have to have is that out of many possible choices, which one is gonna be the best? Which one is gonna be the best? Like, it means optimization problems. Remember the definition of optimization. We want to find the best solutions out of some of the candidates. So you guys can guess that the perceptron is going to be optimization problems because we want to find the best one out of many possible choices. Okay. We're gonna utilize the distance informations, and I mean later on. Intuitively, we wanna hyperplane having the maximum margins. I mean, margins are probably you guys in like margin. That means that if we have the data like these margins. Want to maximize that. That means I want to put the hyperplane in the middle. Maximize the margins and put them in the middle, they are talking about the same things. So we will see this when we discuss SVM. Okay. So let me stop here for the. We're done with the perceptron. And any questions so far before I move to SVM? Move on to SVM. For classification, any given data points, and if you decide to apply the classification, you guys are not gonna use a perceptron at all. The reason why that I introduced perceptron as a starting point is it's good to explain what the classification is. This is kind of the only motivations. So again, it's probably SVM and logistic regressions. That's something that I want to explain it. So, and later on, you guys gonna use that for your own classification problems.